All right, this video is going to be about our final integration method. It's called partial fraction decompositions. We're going to investigate these partial fractions. So we'll start off with just talking about the general principles of what partial fraction decomposition really means and also why we're doing it. And then we'll focus on three different types: simple linear factors, repeated linear factors, and irreducible quadratic factors. And by the end, we should have a general idea of how this is going to work if we keep extending things. You'll see what I mean. Let's jump into it. So this is the general idea. We have these fractions right here that we can add together. Adding fractions is not that difficult. We need common denominators. Our common denominator is going to be, in this case, x plus 3 times x plus 1. So the way that we get that is by multiplying x plus 1 on the numerator and denominator of our first fraction, multiplying x plus 3 on the numerator and denominator of our second fraction, and then we can just add these fractions. This numerator is really 3x plus 3. This numerator is really x plus 3. You can see that when you add this together, 4x plus 6 over x squared plus 4x plus 3, that's what we get when we multiply everything in this denominator. No big deal. We know how to add fractions. This isn't that interesting. But what is interesting is that, in general, if we set this up with integration, then what we'll notice is that the far right side, this integral of 4x plus 6 over x squared plus 4x plus 3, is harder to integrate than the left side. Here, we can see pretty easily that we're just some quick u substitutions away from some natural logs. That's not hard. We can do that really quickly because that u substitution and that natural log form is relatively obvious. Over here, though, we don't really have a nice way of getting things started on all this. There's some things that you can do, but they end up being tricky. So partial fractions is really about reversing this addition of fractions, seeing if we can take something that's already written as a sum and break it apart into some smaller pieces. That way, we might have an easier time integrating things with those smaller partial fractions. So again, we can just kind of move forward here, and that's our general principle. Sums of rational functions are easier to integrate before we add things together, mostly. So if we have smaller, littler fractions, it's likely easier to have things written in that form, meaning if we can undo that addition, that'd be really, really nice for us. So we're going to start off with simple linear factors. That was this example that we have. We're going to set up a process to try and undo this fraction addition. We'll talk about what the simple linear factor means, but let's just start with this example. So for something like this, we have to try and imagine what might have been added together to get this rational function. To do that, we should focus on the denominator because we know that when we add those fractions together, we have a common denominator. So what rational fractions could we have had? Let's focus on this x plus 1 and x plus 3 in the denominator. And oops, that's a little too far. What we'll notice is that if we make a common denominator out of these two pieces, then the things that were added together have to be over those denominators. You could technically get something with a combination like this, but then we could go ahead and split this one up. So either way, we're going to end up with two fractions with a denominator of x plus 1 and a denominator of x plus 3. And that's what I've got written here. What we need to do then is focus on the numerators of these now. Once we know the forms of these things, we need to try and solve for what's in the numerator. We're going to say that there's just a constant up in the numerator. The reason is that if it wasn't constant, if we had a linear piece up in the numerator, like maybe an x plus 2 over this x plus 1, then what we could do is do some long division, and we could write this as 1 plus 1 over x plus 1. So we're going to be just focusing on something like this. We know that we can't get a total sum of like 1 plus all that stuff because the degrees here are smaller than the degree on the bottom, right? If we just look at these first terms, we can clearly see that whatever this is, it's less than 1 in terms of degrees. So we just have to be a little bit careful about all that stuff. Anyways, all that to say, let me get rid of this. All of that to say, we can go ahead and start focusing on how to find these, and it's not a difficult thing to do. Let's just add these together. We're going to do it in the same way, that we added fractions earlier. Let me start that over. Say this is equal to a over x plus 1, and I'm going to use different colors here. I'm going to multiply this fraction by x plus 3 in the top and x plus 3 in the bottom. And then I've got b over x plus 3, and I'm going to multiply my other denominator, x plus 1 in the numerator and denominator. And all this to say ax plus 3a plus bx plus b over x plus 1, x plus 3. That is still equal to this first fraction. Now, the denominators are already equal, so all this to say this numerator is equal to our numerator 4x plus 6. Okay, so this can give us a system of equations, because we know that to combine these numerators together, we have some like terms, we have some linear terms. Ax plus bx has to equal 4x, right? This piece here plus this piece has to be 4. And we also know that 3a plus b has to equal 6. So we can go ahead and take this and translate that into a system of equations that says a plus b equals 4, if we just look at the coefficients of those linear terms, and 3a plus b equals 6. And in your high school algebra classes, you focused on solving these little systems of equations. You could do like a substitution method or an elimination method or something like that. There's lots of stuff that you can do. Maybe if we do that elimination method, we could do some like subtraction here, right? Our first line minus our second line. And so then we have negative 2a equals negative 2. And we can see pretty clearly here that a is equal to 1. And if a is equal to 1, then that means that 1 plus b equals 4, so b is 3. All right, so what did we really just do? We said this integral is equal to a, which is 1, over x plus 1, plus b, which is 3, over x plus 3. All right, notice we haven't actually integrated yet. All we've done is made this look easier to integrate. So partial fractions is less about finding antiderivatives and more about noticing that it's going to be easier to find antiderivatives if we're able to split these rational functions up. Solving these linear systems of equations is kind of annoying, so I'm going to show you another method of doing this that's a little bit faster. These systems of equations, these numerators, so maybe I'll just go ahead and write out that numerator bit again. It was a times x plus 3 plus b times x plus 1. Right? Those were our numerators. A times our other denominator, x plus 3, plus b times the other denominator, x plus 1, equals the actual full numerator. So this is the equation that we were working on, right? And we multiplied everything out, and then we were able to set up a system of equations with linear and constant pieces. What we're going to do instead is just notice that this equation is true for all x values, and so it's going to be true for some specific x values. So let's take a look at two specific x values. Let's take a look at what happens when x is equal to negative 1, and you'll see why. We're going to say a times negative 1, maybe I'll put this in red still. I'll keep all the colors in there. I like them. Negative 1 plus 3 plus b times, and here you'll see what happens, negative 1 plus 1, ooh, that's going to be good news for us, equals 4 times negative 1. There we go, plus 6. So I'm just evaluating this equation at -1. And if we do that, we're going to see pretty clearly we get 2a equals 0, or sorry, plus 0b equals 2. All this to say, a is equal to 1. Now we can do the same kind of thing. I'm running out of room. Maybe I'll do this over here. Let's see what happens when x is equal to -3. We're going to set this little piece equal to 0. Suddenly we've got 0 plus b times -3 plus 1. Well, -3 plus 1 is -2. And that's going to be 4 times -3. That's -12 plus 6. So I've got -2b equals -6. b is equal to 3, meaning our integral is still 1 over x plus 1 plus 3 over x plus 3 dx. So that's really nice for us. So what we'll notice is that we can go ahead and be a little bit clever about how we solve this equation. Instead of trying to solve it in general for a general x value, let's just pick some specific ones that are going to set factors equal to 0, so huge chunks of this equation go to 0. So instead, we can just look at small little portions like 2a equals 2 or -2b equals -6. Those are really easy equations to solve for these a and b coefficients. One more way of doing this. This is just a simplified short version of that little equation that we just did. This is called the Oliver-Heaviside cover-up method. Or sometimes people will call it the Heaviside thumb method. And that's because what we're going to do is we're going to pick the 0 from a denominator and cover that factor up, evaluate the rest. This is kind of a confusing thing, but let me show you what I mean. We're going to look right here for a. We're going to use x equals -1, and we're going to cover up the corresponding factor, this x plus 1 here, and we're going to go ahead and evaluate the rest with a equal to with x equal to -1. So we'll say, all right, 4 times -1 plus 6 over -1 plus 3. That's -4 plus 6 is 2 over 2. That's 1. What you'll notice is that that's exactly what we did over here with our equation when we were solving for a by putting in -1. We put -1 in because that was the factor that got multiplied by b because it was in the denominator of a. Okay? So then that got rid of this term, and we were left with this x plus 3 evaluated at -1, and we just ended up having to divide that. So the Oliver-Heaviside cover-up method just gets around having to set up the equation. Let's get rid of this, and we'll do the same thing for b. For b, we're going to cover up this factor, and we're going to evaluate the rest at -3. This is -12 plus 6, which is -6, and -3 plus 1 is -2, and there we go. B is 3. So this is a pretty quick way of getting these coefficients for these simple linear factors. Oops, I was going to write a b here, but b is 3. There we go. Again, all of this so that we can just look at it really quickly and say, hey, I know what our antiderivative is. Our antiderivative is natural log of x plus 1 plus 3 natural log of x plus 3 plus c. All just to make our integration pretty easy. So we're going to use this method as much as we can for these simple linear factors. So here's another example. I will set up the partial fraction forms for us. We're going to say that this is equivalent to just saying some coefficient over x minus 1 plus some coefficient over x minus 5 plus some third coefficient, we'll call it c, over x plus 4. Notice once we have this, the antiderivatives are going to be a cinch. We're just going to be looking at a whole bunch of logs here. So pause the video, see if you can use that cover-up method, or write out an equation if you'd like, and then pick some x values carefully to get rid of a bunch of terms and solve for these coefficients. Go ahead and pause the video and do that now. All right, seriously though, do it. All right, so this is just my work doing that heaviside cover-up method, right? Follow through that if you didn't get these three coefficients. But now what we can do is just write our integral as -½ over x minus 1 plus 5/2 over x minus 5 plus 1 over x minus 4 dx. And each of these is just a quick little u substitution away from a logarithm. Now, you can use properties of logs to write this in a whole bunch of different ways, right? You can take all these coefficients here and bring them up into exponents, and then you can say, oh, look, we're adding all these, so that's going to be multiplication. So if you wanted, you could end up with something like x minus 5 to the 5/2 times x minus 4 divided by the square root of x minus 1, and put it all together into one log. You could do that if you wanted. That is fine. You might see solutions written that way, but I'm okay as just this nice little linear combination of logarithm functions. So that should work out pretty well. Okay, so what happens if we have repeated linear factors? Well, first off, we should explain what the heck we're talking about with repeated linear factors, and then we'll get into it a little bit. So what we're going to say is that x minus 1 is a repeated linear factor because it has an exponent. Now, okay, yes, there's an exponent on all the factors. It's 1 for most of them. But in this case, we're going to say, all right, we have an exponent, n. We normally think of that as a natural number, so a positive integer bigger than 1. All right, so how does that impact things? Well, what that's going to do is it's going to make us have a couple of options for the denominators of the fractions that we're adding. So here are two possibilities that we have. We could say that this integral, or maybe at least the rational function inside that integral, is a combination of two fractions, one of them with a denominator of x plus 2, and one of them with a denominator of x minus 1 squared. Your common denominator is x plus 2 times x minus 1 squared, so that works. But notice that it could also have this other term with an x minus 1 in the denominator, because the common denominator here, or maybe we'll say the least common denominator, is still x minus 1 squared times x plus 2. We would have to multiply an x minus 1 squared on this first fraction. We'd multiply an x plus 2 and an x minus 1 in the numerator and denominator of the second fraction, and we'd multiply an x plus 2 in the numerator and denominator of this third fraction to make it all match, but it would work. We could say that this is some combination of three different fractions, all with unique denominators. So let's just account for the possibility of this term in the middle here, this linear x minus 1, and we'll figure out what's going on there. So the main note for repeated linear factors is that we have to account for the possibility of all of the exponents up to and including, in this case, 2. If that exponent was bigger, we'd have more of these linear factor things. So let's do this. We'll go ahead and we'll set this up into our partial fractions, a over x plus 2, b over x minus 1, and c over x minus 1 squared. What we're going to do now is figure out what that equation of the numerators is going to be. We have to multiply an x minus 1 squared on the top and the bottom of this one. We have to multiply an x minus 1 and an x plus 2 on the top and the bottom of this one. And on this last piece, we have to multiply just an x plus 2 on the top and the bottom. Now, we don't really care about the denominators, because notice you're going to get x plus 2 times x minus 1 squared in all three of these. But what this means is that a times x minus 1 squared plus b, whoops, I don't want a green parenthesis, I want a red one, times x minus 1 times x plus 2 plus c times x plus 2 is equal to our original numerator of 3x squared minus 3x minus 9. What you'll notice is that now we can do some of the kind of tricky pick an x value to make things work setup, right? Notice if you put in an x value of 1 into this, then we get a times 0 plus b times 0 plus c times 3 equals 3 minus 3 minus 9. And this gives us 3c equals negative 9. C is equal to negative 3. We can do a similar thing with x equals 2, or negative 2, sorry. If we do that, what you'll notice is that we've got negative 2 minus 1, that's negative 3 squared, so this is 9 times a, plus 0b plus 0c, right? They both have this factor of x plus 2 on them. If we throw in negative 2, those are going to go to 0. And then on our right side of our equation, we've got 3 times 4. Negative 2 squared is 4, so that's going to be 12 plus 6, right? Minus 3 times negative 2 minus 9. So we've got 9a equals 12 plus 6, that's 18, minus 9 is 9. So look at that, a equals 1. Notice that there's not a nice x value that we can pick to get the b coefficient. What that means is that if we went back to the very beginning, you can do the cover-up method. You can cover up, oops, not here, sorry. You can cover up the x plus 2 and evaluate the rest at negative 2, and what you'll get is 1, and that's for a. Similarly, you can cover up this x minus 1 squared and evaluate the rest of this fraction at positive 1, and that'll give you the coefficient for c over the x minus 1 squared. We won't be able to get the coefficient for b this way, but all is not lost. We have some more work that we can do. All right, let me write down my stuff. I had a equals 1 and c equals negative 3. All right, cool. So if we go ahead and rewrite the equation for numerators, what we now have is that instead of a being multiplied by x minus 1 squared, we have 1 being multiplied by x minus 1 squared. We still have that b is going to be multiplied by x plus 2 and x minus 1. But now, instead of c being multiplied by x plus 2, we have negative 3 being multiplied by x plus 2. We'll just update what we know. And now what you can do is a couple of different things. You can either just evaluate this at some other x value that's not 1 or negative 2. You could put 0 in here if you wanted. And what that will do is it'll give you an equation that only has b's and numbers in it. And you can solve for b. Another thing that you can do, and I like being in the habit of this, is to just group some like terms. So what I might do is look at the quadratic terms, the degree 2 terms. The quadratics are going to be 1 times x squared, because this is an x minus 1 times x minus 1. We've got b times x squared. Notice there's no quadratics here, only linear stuff, and that should be 3x squared. So suddenly we can see really easily 1 plus b equals 3. B pretty clearly has to be 2. You could do this same thing with like the constant terms. Instead, you could say, okay, negative 1 times negative 1 is 1 times 1. Then we've got b times 2 times negative 1. Then we've got negative 3 times 2, and we've got that equal to negative 9. And you can see pretty clearly here as well that 1 minus 6 is negative 5. If you add 5 to both sides, you're going to get negative 4. And so we've got that b is, again, equal to 2. Either way is fine. All right, so if b is equal to 2, then suddenly this integral, let me move this thing out of the way so I've got a bit more room, then suddenly our integral isn't too bad. It's the integral, I'll do it in black, of 1 over x plus 2 over x minus 1 minus 3 over x minus 1 squared. The only difference is that this is not a log anymore. It's a power function, right, with a negative 2 exponent. So we've got the log of the absolute value of x plus 2 times the log of the absolute value of x minus 1. But if you want to think of this term as really 3 times x minus 1 to the negative 2, then you can do a quick little u substitution where you end up adding 1 to both, or to the numerator and denominator. I should put the negative. Sorry, I'm all mixed up. I need to put that negative coefficient in here. Adding 1 to the exponent and dividing by that number. So this is going to be positive 3 over x minus 1 to the negative 1, right? Exponent now, so it's just in the denominator with a exponent of 1. I think I stumbled over that, but you know what I mean. All right, so not a log, but it's still easy to do. Cool. So for repeated linear factors, you can get all of the simple linear factor coefficients and the high exponent coefficient, but you're going to have to do a little bit of work to find whatever's left, this b. As a quick summary, we'll just notice that if we introduce higher and higher exponents, you're going to need to introduce all of those integer value exponents up to and including. So if you had something that was over, instead of an x minus 1 squared, if this was over x minus 1 to the 5th, you'd have a lot of work to do. You'd have to include something over x minus 1, something over x minus 1 squared, something over x minus 1 cubed, over x minus 1 to the 4th, and over x minus 1 to the 5th. Now, it's possible that some of those coefficients are 0. It's possible that when we solve this stuff, way back to our beginning setup where we weren't really sure, it's possible that this could be 0. And if it is, then we really do just have those two fractions in that first line. But we have to account for the possibility that it's not. All right, let's move on to irreducible quadratic factors because this video is already getting kind of long. So the question is, what if we can't factor things into linear factors, whether they're simple ones with an exponent of 1 or repeated ones with bigger exponents? So we again need to account for the different possibilities in the numerator if our denominator is quadratic. We might just have a constant. You might just have something like 4 over x squared plus 1. But we could have something like 4x plus 1 over x squared plus 1. This is still a fraction that can't be like reduced. We can't do long division on this and write it as something else. Earlier, we said that our numerators were constants because the fractions had linear pieces in the bottom. Now, though, if we give the possibility of linearity in the numerator, because there's a degree 2 thing in the denominator, we're just going to end up with more coefficients. So here's our general idea. With these irreducible quadratics, a times x squared plus b times x plus c, where you can't factor that nicely anymore, we can't split it up into just linear pieces, we have to give the possibility of some linear numerator. So we have 2 coefficients to find for this now. All right, so let's give this a shot. We'll set up our partial fractions. Maybe I'll just write it off to the side here. This is going to be an integral of, whoops, not 7. What am I doing? A, we'll call it, over x minus 2 plus bx plus c over x squared minus 2x plus 3. You can double check and make sure that we can't factor this. We'd be looking for some values that multiply to get negative 2 and add to get 3, and that's not going to work out very nicely if we're looking for integers. So we can't factor this thing nicely. So we'll call it an irreducible quadratic. Notice we can still do the little heaviside cover-up for a. So we can say, all right, a is going to be what happens when we evaluate 2 into the rest of this. So that's 7 times 2 squared. That's 7 times 4, which is 28. Then we've got minus 13 times 2 plus 13 over 2 squared. So that's 4 minus 2 times 2, which is 4, plus 3. All right, let's check this out. 28 minus 26 is 2, plus 13 is 15 over 3. A is 5. All right, we're getting somewhere. So what we really have is 5 over x minus 2 plus, we can't really do that cover-up method for this linear numerator, oops, minus 2x plus 3. There we go. But what we can do is set up that equation, right? Let's multiply those things together, multiply out with common denominators, add these things together, and that means we're going to have 5 times x squared minus 2x plus 3 plus bx plus c times x minus 2, and that's going to equal 7x squared minus 13x plus 13. Again, what we're really doing is we're taking this denominator and multiplying that on this fraction, and then we're doing the same thing with this denominator on this fraction here. So hopefully that's something that we're okay seeing by now. I know we've only looked at it for 20-some minutes, but this is where we're at. Okay, so what I might do now is go back and do this kind of like quadratic grouping. What I'm going to notice is that if I looked at the linear terms here, I'm going to get a bx times negative 2 and a cx. I'm going to get b's and c's in both of those things. So let me just do a little bit of work and say, if I look at the quadratics only, then that's going to be 5 times x squared, bx times x, and 7x squared. So if 5x squared plus bx squared equals 7x squared, then what we're really saying is that 5 plus b equals 7, and it's pretty clear that b is 2. If we do the constants, then what you'll notice is that those only involve things with c's in them. There's no b's in the constants, right? Because there's an x multiplied by b right off the bat. So I've got 5 times 3, that's 15, plus c times negative 2, equals 13. All right, so we can see here pretty easily that c is 1. Great. So this gives us our new integral, 5 over x minus 2 plus 2x plus 1 over x squared minus 2x plus 3 dx. So what you'll remember is that I said right at the beginning that when we do this kind of thing, we actually don't get the antiderivative. We just get something that should be easier to anti-differentiate. So if we're looking at something like this, I know the very first term is still going to be a nice little log. This one's not bad. This second one, though, I might think carefully about. Normally I'll say, let's try a u substitution, right? Quadratic on the bottom, linear on the top. This sounds great. I know those are generally derivatives of each other. I could say du is going to be 2x minus 2 dx. And I say, oh no, I have a 2x plus 1. Well, one of the things that I like to do is just say like, oh, screw it. Let's make it 2x minus 2. Now, that would be really great for my u substitution, but it's not what our actual integral is. Our integral has a 2x plus 1. There we go. Done. That's 2x plus 1. It's just disguised as 2x minus 2 plus 3. All right, what I'm really going to do is I'm going to separate that as a whole completely different fraction. Ooh, look at that. All right, so for this one, it's our 5 natural log x minus 2. For this middle one, we've got a u substitution, and that's pretty clearly going to end up just giving us another natural log. I'll let you fill in the gaps if you want it. Oops, I need a 2x here. There we go. And now this third one, we may have to think about a little bit. This, maybe it's helpful if we complete the square. So this is really, I'll do this in pink. This is really 3 over x minus 1 squared, but x minus 1 squared would be x squared minus 2x plus 2, so it's really plus 1. And once it's written like this, remember, we're looking to find the antiderivative of that. That's going to be a nice old arctan. We've got a coefficient of 3 on this, and we're going to have the inverse tangent of x minus 1 plus c. So We may end up with some inverse tangents by having to do some completing the square on this if we get just constant stuff over that quadratic piece. That's always a nice strategy. Otherwise, we may end up with some u substitution, or we end up with some logs like we're kind of used to so far. Remember, we don't have to always have logs because we could have an exponent of like 2 or 3 on here, in which case we have a different power function that we're anti-differentiating. So just keep an eye out for all that kind of stuff. All right, last question in this, because again, this video is getting kind of long. How do we extend this further? Well, we're not really going to, because what you're going to notice is that you could consider things like powers on these irreducible quadratics. What if I had an exponent of 3 on here? Well, it happens to be the exact same thing that you would think. We have a copy of an ax plus b, a linear piece, over x squared minus 2x plus 3. Then we have another partial fraction with a linear piece over x squared minus 2x plus 3, all squared. And then we have another linear fraction, or linear piece, over x squared minus 2x plus 3 cubed. We have to build up those exponents just like we would with linear things. And then you could say, well, what if we had a cubic polynomial that we couldn't factor nicely? Well, cubic is degree 3, so in the numerator, make it degree 2 or less. So we have like an ax squared plus bx plus c. And then you could keep going and going and going. So the extensions aren't hard to think of. But what you'll notice is that as we do this, computationally, you're going to have more and more unknown coefficients, meaning you're going to have to set up bigger and bigger systems of equations to solve for those unknown coefficients. That's not difficult to do in general, but it is very, very time-consuming. If you take a linear algebra course, then it becomes less time-consuming. We probably haven't seen much linear algebra up until now, but solving those equations can be very, very frustrating computationally. So we'll mostly just stick with things like quadratics and repeated linear things with not too big of exponents. You could imagine how annoying it would be if I had a cubic polynomial raised to a 10th and I couldn't reduce the cubic, right? I'd have to have all of the 10 different versions with exponents climbing up to 10 of these cubic things that have quadratic stuff in the top. Oh my goodness, that would be terrible to find coefficients for. So we're not going to do it. That's partial fraction decomposition in a nutshell. Hopefully all that stuff makes sense and kind of works with our concepts extending it, even though computationally we won't extend it.